Hello my dear student. Today let us discuss more about properties of Lebesgue integral of non-negative measurable function, some elementary properties. Okay, these are all important properties. We are going to use this property in our further studies. So in fact these are all non-result for our integration calculus, integration in graduation level, integration in calculus, class 12 level integration in calculus. But we are going to prove this result in our new setup, that is Lebesgue integration, in our new setup. Okay, so first let us do one important example, then we are going to prove this these four result. Number one, this is number one, number two, number three, number four. These are very important elementary properties of Lebesgue integral of a non-negative measurable function. So before that, let us do one important example. So what does the example says? Let us see. It is very important, so that if f is a non-negative measurable function, then the function is equal to 0 almost everywhere. We have already learned what is the meaning of almost everywhere. Let me repeat again. The function is 0 everywhere, so except a set of measure 0. That means the function is not equal to 0 on a set whose measure is equal to 0. Okay, that is the concept of f is equal to 0 almost everywhere. The function is 0 everywhere wherever the function is not equal to 0. The set of point of those, the collection of those points, its measure is equal to 0. So that is the concept of f is equal to 0 almost everywhere. Then the example says that f is equal to 0 almost everywhere if and only if integration of f dx is equal to 0. So what does it say? It says that if the integration of a function is equal to 0, then the function is equal to 0 almost everywhere. Conversely, if the function is equal to 0 almost everywhere, then its integration is equal to 0, or its Lebesgue integration is equal to 0. Okay, so this is the first example. Yeah, very important. Okay, so solution, suppose first let us assume that the function is equal to 0 almost everywhere. Okay, suppose the function is equal to 0 almost everywhere. So then according to the definition, how we find the integration of the function f is just we think about simple measurable function phi, collection of all simple measurable function phi, such that phi is less than equal to f, and you take the supremum of those phi, and that is equal to the integral f. Okay, so that is the integration of f from the definition. Okay, then just think about the simple measurable function f which is less than equal to f. Okay, so this phi being less than equal to f, and f is non-negative, phi is also non-negative. Okay, then definitely phi is also equal to 0 almost everywhere. Then it is clearly what do we have? Integration of phi dx is equal to 0. So for all those phi or simple measurable function which is less than or equal to f, so its integration is definitely equal to 0. So all are 0. The supremum is also 0. Okay, so yeah, this let me explain a little bit in this one. So what we have a function, we have a function f, we have a function f, and phi is less than equal to f, and phi is non-negative, f is also non-negative. So what the function says? The function says that the function is equal to this is equal to 0 almost everywhere. Almost everywhere means the collection of the points such that the function is non-zero, when it is greater than 0, this set, okay, its measure is equal to 0. So there are maybe some point where the function is not equal to 0. So the collection of all those points, its measure is equal to 0. It says that. Okay, but the phi is a simple function. Okay, the phi is a simple function. Then you know how you can write phi. Phi is equal to, say, summation I is running from 1 to n ai, and then chi ai, chi capital AI. This is the definition of simple measurable function. Okay, so this phi is less than f, but f is equal to 0 almost everywhere. All right, so wherever the function is not equal to 0, then its measure is equal to 0. Wherever the function is not equal to 0, its measure is equal to 0. So phi being less than equal to f, whenever ai is not equal to 0, the measure of the set ai must be 0. All right, because phi is less than equal to f, and f is equal to 0 almost everywhere. So wherever the function is not equal to 0, its measure should be 0. No? Phi is less than f means what? Whenever ai is not equal to 0, its measure of capital AI must be 0. Okay, so that means then integration, what is the integration? Phi dx is equal to summation I is running from 1 to n ai. So one thing you have to say, remember, all ai's are 0, and wherever ai is not equal to 0, measure of capital AI must be 0. That is coming from the definition of almost everywhere is equal to 0 for the function f, and that the function f is bound greater than equal to the simple measurable function phi. So this is true. So one thing is sure, either ai is, this small ai is equal to 0. Whenever small ai is not equal to 0, measure is equal to 0. Okay, that means this is 0. So what is the conclusion? So whenever you think about one simple measurable function phi which is less than or equal to f, integration of that simple measurable function is equal to 0. So all are 0, right? The supremum is also 0. All the integration of all such simple measurable function is equal to 0. Therefore integration of f is equal to 0. So integration f dx is equal to 0. Okay, so what is the conclusion? The conclusion is when the function f is equal to 0 almost everywhere, integration of that function is equal to 0. Okay, integration of this function, f is equal to 0. So next, conversely, let us assume that integration of a function f is equal to 0. The function is non-negative measurable function, its Lebesgue integral is equal to 0. Now let us prove that the function is equal to 0 almost everywhere. Let us prove that the function is equal to 0 almost everywhere. Okay, so conversely, let us suppose that integration of f dx is equal to 0. Then for its natural number n, let us define the set en. Okay, so this is the set of point x such that f of x is greater than or equal to 1 upon n. Okay, what is capital En? Capital En is a set of point where the function f of x is greater than or equal to capital N. So that means what? F of x is, from this definition of En, f of x is greater than or equal to n on the set En, right? F of x is greater than or equal to 1 upon n on the set En. That means what? F of x is greater than or equal to 1 upon n chi En. Okay, you can put the characteristic function chi En. All right, so that means what? So this is what? This is a simple function. Okay, simple measurable function. This is constant and En is a set chi En. So So this is a simple measurable function, and En is measurable because this function is measurable. En is also measurable. So this is a simple measurable function which is less than f of x. Okay, so how you find out the integration of function f of x? You think about all those simple measurable function which is less than or equal to f, then you find out the supremum. So this is one of the candidate of the simple collection of simple measurable function which is less than equal to f of x. Okay, therefore integration of this one must be less than integration of this one. All right, so this is a simple function which is less than f of x, therefore integration of f of dx is greater than or equal to 1 upon n integration. So integration of this simple function is what? 1 upon n measured En. All right, but this is equal to 0. That means what? 1 upon n measured En is less than equal to 0. That means since measure of a set cannot be negative, so it should be 0. This is 0. That measure of En is equal to 0. All right, measure of En is equal to 0. So one thing you can establish easily. The set of point x such that f of x is strictly greater than 0 is equal to n is going from 1 to infinity En. So this thing you can establish. Let us see how it works. Let us see. Here again, let's go back to the window. Yeah, so what we want to show is that and the x such that f of x is strictly greater than 0, this is equal to union n going from 1 to infinity En. All right, so what is the normal method? You take 1 point from here and show that it is a member of this one. So you take 1 point from here. You take 1 point from here. Suppose x is a member of this one. Okay, if that happens, what? F of x is greater than 0. So if f of x is greater than 0, then by Archimedean property, there exists one natural number such that f of x is greater than or equal to 1 upon n. So that means what? This implies that x is a member of En. So whenever you take 1 point from here, that point is a member of En. Since it is a member of En, it is the member of this union. Okay, so this established. So conversely, you take 1 point from here. Then what happens? X will be a member of, you take 1 point from here, from this union, then x must be member of some member, oh sorry, again start. So if you take 1 point from here, then this x should be member of some member of this union. Okay, so if x is a member of En, what happened? According to the definition of En, f of x is greater than or equal to 1 upon n, but 1 upon n is a non-zero number. It is strictly greater than 0, so f of x is greater than 0. That means what? X is a member of this set. So the equality of these two set established. Okay, the set of point where the function is non-zero is equal to union n going from 1 to infinity En. Okay, so this equality established. And then let us see the measure. Then let us see. So this equality established. So then from the theory of the measure, a measure is countably subadditive. Okay, so measure of this one is less than equal to measure of the sum of the measure of the En, but measure of En is equal to 0 for each n. Okay, we have already shown measure of En is equal to 0 for each n. So then what does it say? And the set of point where the function is not 0, its measure is equal to 0. Then by definition of almost everywhere, what we have is that f of x is equal to 0 almost everywhere. Okay, so whenever the integration of a function is equal to 0, so what is the conclusion we draw? The function is equal to 0 almost everywhere. Okay, so this completes the proof of the example, and this is very important example. Next, let us go to the theorem. So So let us see. The statement of the theorem is that, you know, we have two non-negative measurable functions, f and g. So f and g are two non-negative measurable functions, and this is page number. Okay, then number 1 says that if f is less than or equal to g, then integration of f is less than or equal to integration of g. Okay, this is Lebesgue integration. If a is measurable set, if a is measurable set and f is less than or equal to g on the set A, then integration of f on set A is less than or equal to integration of g on the set A. Okay, so this is the number 2. So number 3 says that what? If a is greater than or equal to 0, then integration, you know, the function is multiplied by a is equal to, you multiply the integral of the function. Okay, so this constant can be taken out from the integration. Okay, this is, you know, usually this is in our graduate level calculus, we know it. Okay, but here in the new, you know, context, Lebesgue theory of integration, we are going to prove this one. Okay, so and lastly, if a and b, if a and b are measurable sets and a is a superset of b, then integration of f on the set A will be greater than or equal to integration of the same function f, okay, on the set B. Okay, this is the same function but the domain is bigger, therefore the integration is greater than. Okay, so this is the, you know, number 4. Yeah, let us now prove it. It is not very hard. Okay, just you have to recall the definition. That's why I told you, I gave you enough time to recall the definition, to read it properly. Now we are going to use it. So let us see proof number 1. So if phi is a simple measurable function such that phi is less than or equal to f. Okay, what do we have? Number 1, in number 1 what we have? F is less than or equal to g. If phi is a simple function less than or equal to f, then phi is also a simple function which is less than or equal to g. Alright, so then phi is also a simple measurable function which is less than or equal to g. Alright, then therefore supremum, you know, supremum phi dx, phi is less than or equal to f, is less than or equal to supremum phi, okay, less than or equal to g, yeah, integration phi dx. So this is obvious. Okay, but this supremum is equal to f dx and this supremum is equal to f dx. So how does it work? Let us see again. You know, in the pen window, let us go back again in the pen window. Let me explain again here. Suppose you have this collection, then you have this collection. Okay, the whole collection is for g. All right, the whole collection is for g, you know, here. This is for g. Now whole collection is for g. Yeah, whole collection. What the collection? It is the collection of, you know, and this is integration phi dx, where phi is less than or equal to g. All right, so since g is greater than or equal to f, suppose this much small domains, this much is, you know, those, this much, where this is small domain, in this small domain what you have integration of simple measurable function which is less than or equal to f. Okay, all right, the this is small domain. Small domain contain what? It is the set of integral of simple measurable function which is less than or equal to f. Okay, so less than equal to f means less than equal to g, no? So it is a member of this whole domain. So if you take the supremum of this small domain, obviously that will be less than equal to supremum of bigger domain containing the smaller domain. All right, integration of bigger domain, this one will be greater than equal to the supremum of this smaller, right here. Okay, so what I want to tell you that you have a set of real number, and this is the set of real number, then you have a bigger set of real number consisting of the earlier set. All right, so if you take the supremum of the bigger set, that supremum will be greater than or equal to the supremum of the earlier smaller collection set. So therefore what is the conclusion? Since since the function f is less than or equal to g, so whenever you take a simple measurable function which is less than or equal to f, that is going to be also a simple measurable function less than g. Okay, so the domain from where you are going to take supremum of the simple measurable function for the function g is greater than or consists of all other simple measurable function which is greater than or equal to f. Okay, so therefore what we have, we have this we have this inequality. So what is this? This is the supremum of all those phi which is less than or equal to g, and this is the supremum of all those phi which is less than or equal to f. So the domain from where you are going to take the supremum of this one consists of all other contains the domain from where this supremum is going to take. Okay, therefore supremum of this bigger domain will be greater than supremum of this domain. So this is obvious. All right, this is obvious. Okay, number two, it is given that f is less than or equal to g on a. On the set A, the function f is less than or equal to g. All right, and then if you multiply by characteristic function is non-negative. Okay, so if you multiply both sides, this inequality maintains. Okay, so this is true, and that means what? According to number 1, by 1, if a function is greater than another function, the integral of the function is greater than this one. Okay, then integration of this one is less than or equal to this one. But according to the definition, what is this integrand? The integrand, you can integrand of the function f on the set A is less than or equal to integration of the function g on the set A. So this is what we wanted to prove. Okay, so number 2 is also established easily. And next is number 3. Let us see number 3. What do we want to show? We want to show that equality of these two. Integration of the function af dx is equal to a being constant can be taken out of the integration f dx. Okay, we want to establish this equality. So if a is equal to 0, af is equal to 0, and then whatever value it has, if you multiply by 0, it is also 0. So equality is established, and it is obvious. If a is equal to 0, it is obvious, it is done. Okay, and now let us consider the case when a is not equal to 0. If a is not equal to 0, then suppose phi is a simple measurable function with phi less than or equal to af. Okay, so you are going to find out the integration of the function af. F is a function, it is multiplied by a constant, and f is also a function. Now you are going to integrate the function af. Then you have to think about the simple measurable function phi which is less than or equal to af. So whenever you take one simple measurable function phi which is less than or equal to f, you have this one implies and implied by, since a is non-negative, if you divide both sides by a, the inequality maintains. 1 upon a, phi will be less than f. Okay, so a simple function is multiplied by a non-negative real number. The resulting function is also a simple function. Okay, so what does it say? Whenever you have a simple measurable function phi which is less than or equal to f, you have a simple measurable function psi which is less than or equal to f, and the simple measurable function psi is nothing but a psi is equal to phi, and psi is less than or equal to f. Okay, so what is the meaning? whenever you take a simple measurable function phi which is less than equal to af, you have another simple measurable function psi which is less than equal to f, and si is equal to how much? Si is equal to phi. Okay, this is implies and implied by. Okay, so this is the thing you have. Then what happened? So integration of the function af is equal to, it is a supremum of phi, supremum of integral of phi dx, where phi is less than equal to af. Okay, so phi is less than equal to af means what? Psi is less than equal to af. Okay, so supremum of si phi means what? Phi is equal to si. Okay, supremum of si dx, psi is less than equal to f. This is true. Then for a simple measurable function, if it is multiplied by a constant number a, the constant can be taken out of the integration. This we have already done. And a is non-negative. This supremum is also doesn't change. Okay, so that means what? You take out a outside the supremum, you will get this. But what is the supremum of this one? Supremum of psi, integration psi dx, where psi is less than equal to f, is the integration of f. Okay, so af. So that means what? Af dx is equal to af dx. Okay, so this very simple, but we are using the definition, okay, very clearly. So you don't take it lightly. You read it again and again, and then you write yourself, that you will understand. Number 4, let us see. If a is a superset of, if a is a superset of b, then characteristic function of a will be greater than equal to characteristic function of b. This is all right. Okay, this is obvious. All right, that means what? If you multiply by the non-negative function, f is non-negative, so this inequality maintains. Okay, f is non-negative. If you multiply by this one, it is, this inequality maintains. That means what? We have already done by number 1, that if a function is greater than another function, Lebesgue integral of that function will be greater than the Lebesgue integral of the second function. So but this one is what? This one is by definition integration of the function f over the set a, and this is what? This is integration of the function f over the set b. So if a is a bigger domain than b, then integration of the same function f is greater than equal to on the smaller domain. So this is the thing. So next is a little bit lengthier theorem, very fundamental theorem in measure theory, Fatau's lemma. So next, this week I am going to give attention to 4th semester. So this is the last class for this week. Okay, so next time when we meet, we will talk about Fatau's lemma. Okay, so okay, thank you.